Okay, today is all about block cipher modes of operation. So we're going to actually design it together, and we're going to use block cipher encryption as a building block to try and build something that's more general purpose and also hopefully achieves IND-CPA security. So this picture shows the block cipher you've already seen. It takes in a key, it takes in a plain text, and it outputs ciphertext. We've already seen this. But one big problem is that this is limited to encrypting 128-bit messages. If your message is any other length, the function is undefined. It doesn't know how to encrypt messages of different lengths. So what if I had a message that was longer? Say it was 256 bits instead. To try and predict what I'm about to do to encrypt a longer message that is 256 bits instead of 128. Well, I notice that 256 is twice as many bits. So if this lets me encrypt 128, I could just use AES twice, take the first half of my message, encrypt it with the block cipher and a key, and then take the second half of the message, encrypt it with the same block cipher and the same key, and I get the second half of my ciphertext. That's the first half, that's the second half, and that should work OK. So that's one possible approach to encrypting longer messages, is to use AES multiple times to encrypt each chunk of my message. And remember, we want to use the same key every single time. The reason here is because if I had to use different keys every single time, I'm back to the one-time PAT situation where I have to exchange new keys for every single message, and that's not practical. Remember, the point of block ciphers was to use one key to encrypt lots of messages, so I still want that to be true. That's why we're using the same key for both halves of this message. So believe it or not, we're actually done. This is actually your first block cipher chaining mode. It takes the block cipher as a building block, and it extends it to encrypt messages of different lengths. This one is called ECB mode. That's what they named it, and you've actually just designed it. In equations, it would look something like this. You would have to take all of the ciphertext outputs and concatenate them together. This double bar is concatenation, so now you know. And there's some more symbols, but I think the picture makes this more intuitive. It is just using AES multiple times. Unfortunately, we can't stop here because we still haven't achieved IND-CPA security. So what is the one word that explains why this scheme isn't IND-CPA secure? Deterministic. Okay, great answer. So I think this is not IND-CPA secure because it's deterministic. If I encrypt the same thing 10 times, I will get the same output 10 times. And that's a problem. We've already seen that that fails the IND-CPA game. Since this game is deterministic, an attacker can win the IND-CPA game, which shows us that this scheme doesn't meet our definition of confidentiality. So it solved one of our problems, allowing us to encrypt longer messages, but it didn't solve the IND-CPA problem. So we have to go looking for other schemes. But this is one possible scheme you could use. So an example of why ECB is not IND-CPA secure is to remember the penguin. So this is a penguin. It's a picture. And what if I took every pixel of this picture? So I took the top left pixel, which is white, and then I take this pixel, and then maybe this one, which is black, and that one, which is yellow. I take every pixel separately, and I use ECB mode, this encryption, to encrypt every single pixel separately. So I treat every pixel as a different message, and then I pass it into ECB mode. Well, the result, and remember the goal is to try and achieve confidentiality, so I don't want attackers to be able to see the penguin. I want to send something scrambled over the network. So if I take every pixel and I encrypt it using ECB mode, where I feed each pixel as a chunk you can imagine into ECB mode, here comes the result. Well, it's kind of secure. It doesn't look like the original. But if you're an attacker, can you kind of guess what was encrypted? Yeah, you sure can. I can still kind of see the penguin. So remember the penguin if you're wondering why ECB mode and deterministic schemes in general aren't secure. This picture tells you why. All of the black pixels got encrypted to the same different color, and all the white pixels got encrypted to the same different color. So when schemes are deterministic, you leak information about which bits are identical, and we can still kind of see the penguin sitting there. So this scheme doesn't provide the security we're looking for.